Let's just discuss chapter number 3, which in which we will discuss operational amplifier, DC effects and limitation. In other words, we're going to discuss in this chapter how operational amplifier um, behaves at DC, that is when the frequency is 0, or at a very low frequencies. Actually, in this chapter, basically we're going to look at how the assumptions that we were using in the last chapter about the ideal operational amplifier are going to be pretty close to the practical values of the open loop gain, input resistance and output resistance of inverting and non-inverting amplifiers when you assume that your open loop gain is not infinity, your input resistance of operational amplifier is not infinity, and your output resistance is not 0. That is, we will assume the actual values of operational amplifier, and then based on those values we are going to derive, perhaps we're not going to do the whole derivation because there's really no use of doing the whole derivation. The whole idea is to see and compare the actual values of different parameters that we discussed in chapter number 2 for different amplifier circuits, how close they will be to their ideal values. That's the basic idea about this chapter, and as you will see that they are just so close that there is really no point at DC. There is no point of using non-ideal values. Ideal values are perfectly fine to be used under all situations if you are operating the operational amplifier at a low frequency or DC value. Low frequency means 5, 4, 6, 7, 8, 9, 10 hertz, something like that. In the next chapter, actually, we're going to look at the AC effects of operational amplifier limitations, in which we will see if you change the frequency, how different values, gain and all those things are going to change, and actually then you will see that the frequency change does make a good amount of difference between the ideal values and the practical values. So in the next chapter, in chapter number 4, is going to be a deeper conversation about the non-ideal and ideal situation. In this chapter, as you will see, we will discuss the non-ideal case at DC or low frequency, but since they will be very close to each other, it's perfectly justified to use the ideal situation for DC and lower frequencies. So non-ideal parameters, again in chapter number 2 we discussed that 3 parameters of operational amplifiers: the input resistance, what we are referring here as RD, differential input resistance, because remember the input is differential input in operational amplifier between the positive or non-inverting terminal and the inverting terminal. Likewise, open loop gain of the amplifier A, and the output resistance of the amplifier. So again, we assume that the differential input resistance used to be this, used to be infinity. The output resistance used to be, so this we assume to be infinity, this we assume to be 0, and of course gain we assume to be also infinity or very large. The actual values from the data sheet of 741, which is in your book, as well as you can find it online, the typical value of the input resistance RD is about 2 mega ohm, and the minimum value is about 0.3 mega ohm. And likewise, the output resistance is 75 ohm. It is not 0. Actually, 75 ohm is decent value. It is not 0. And the gain, typical gain of 741 op amp is 200,000. Again, a huge gain, not infinity, but it's still a very large gain. And the minimum value is about 50,000. So a gain can be anywhere between 50,000 and typical value 200,000, can go beyond 200, but generally we assume to be between 200 and 50,000. So if these parameters are assumed, how when you create different circuits like the basic circuits of inverting circuit and non-inverting circuit, how their closed loop gain, their input resistance and their output resistance are going to be affected. That's what we are going to discuss in the first 2 sections of this chapter. So let's look at first non-inverting amplifier. Now we're going to look at these parameters one by one: gain, input resistance and output resistance of these two amplifiers. And when we are discussing gain, input, and output resistance, we will not consider non-ideal parameters, all of the non-ideal parameters at once, because the calculations become really complex if we do that. So for example, for gain, we will assume the non-ideal value of open loop gain A, but we will still assume that the input differential resistance is infinity and R out is 0. So if we do that, and if we do the derivation, again, I'm not going to go into the derivation at this time. There is derivation in the textbook. If you want, you can look at it. I think since we will not be using these equations, to be very honest, at DC, really there is not much point, unless you are interested and you want to see how did you get this equation, then yes, you can look at the derivation, which are not very complex, pretty straightforward derivations, but there is not really much value to go through the whole derivation and then see how did you get it, because again, most of the time we will not be using these non-ideal parameters at DC. We will still be using the ideal parameters at DC, because again, the values are just going to be so close. So anyways, the closed loop gain of the non-inverting amplifier. Now remember, the closed loop gain that we discussed in the last chapter was 1 plus RF over R input, Ri or R, not R input, Ri or R1, whatever this resistance is. Ri you're calling it. It's not input resistance, remember that. The input resistance of non-inverting amplifier is infinity, because remember, input resistance means input voltage divided by input current, right? And then remember, input current, because no current flows into the terminals of operational amplifier, then Vi over I input is infinity. So the input resistance of the non-ideal non-inverting amplifier is infinity. They're calling it Ri, so I'm just going to go with Ri. Generally we call it R1, but whatever, it doesn't really matter. So this is the ideal gain that we derived in the last chapter. Now the non-ideal gain, if you assume that A is non-ideal, it's not infinity, it is given by this equation right here. A is the open loop gain and beta is called the feedback factor or voltage feedback factor. Sometimes you call it voltage feedback factor and sometimes feedback factor is the same thing. Also, A times beta is called loop gain, and it is coming from control theory, and again it is given in the book, complete derivation. Again, I don't see a very a big value in discussing the whole thing, so I'm just giving you the equation, and then we can compare the equation with the ideal and then discuss how wise it is to use the non-ideal equation when the ideal equation is perfectly fine to use, and there's not going to be much difference when you're doing the problems using the ideal equation. Okay, so let's compare these two equations right here. Beta, as you can see, is R input over R input plus RF, or in other words, beta is 1 over ACL, as you can see, ACL ideal, right? Because ACL ideal, this is ACL ideal. ACL ideal is R input plus RF over R input. So this is opposite of that, right? So beta is of course less than 1 based on the values of Ri. No, I keep calling it R input, sorry, I'm sorry. It's not input resistance, it's just Ri. Since it is Ri, I just call it R input, but it is not the input resistance of the non-inverting amplifier. So Ri divided by Ri plus Rf, of course it's less than 1 based on the gain, the ideal gain of your amplifier. Let's say if your ideal gain is 10, then of course, or your ideal gain is 11, let's say, so of course Rf over Ri is going to be 10 plus 1, 11, and Rf can be 1k, Ri can be 100 ohm, Rf can be 10k, Ri can be 1 kilo ohm, but whatever. So in that case, beta is going to be 0.1. If your gain is 100 plus 1, 101, then beta is going to be 0.01. So again, the beta value is going to be 0.1, 0.01, 0.05, whatever. It's not going to be extremely it's not going to be, you know, nano or micro. So if you multiply the value of beta, let's say 0.1 or 0.01, by the value of A, what you're going to get over here, A times beta, or in this one, let's look at here, what you're gonna get in this 1 over A. These are the same equations. We are just dividing numerator and denominator, or we're just taking beta out, and it's gonna become 1 over beta divided by 1 over A beta. So, or actually, let me go back and correct myself. They're dividing the numerator and denominator by A times beta. A times beta. So A times beta is going to be a very large number. Assume A is 200,000, beta is 0.1 or 0.01. It is still going to be 20,000 or 2,000, whatever the value is, right? So 1 over that value is going to be quite smaller than 1. So if we ignore this value with respect to 1, the denominator is just going to become 1, and your closed loop gain is going to become 1 over beta. What is 1 over beta? 1 over beta is 1 over ACL ideal, right? 1 over beta is Ri plus Rf divided by Ri, which is this thing. So basically, under normal values of Ri and Rf, your ACL and ACL ideal and ACL exact. So this is ACL exact or non-ideal. Your ACL exact and ACL ideal for the non-inverting amplifier is going to be very, very close to each other, and you will see that in the example. So is there any point of using the exact expression when your values are so close? I don't see any point, and as you will see, you're not going to see any much difference either. Okay, but in any case, this is the equation, ideal or exact equation. Let's move on to input resistance. So again, I discussed input resistance for the ideal amplifier was, non-inverting amplifier was infinity, because I input is 0 and V input of course is non-zero. So V input over I input, when I input tends to 0, it's gonna give you infinity. So input resistance of non-inverting amplifier, ideally it is infinity. Okay, so for the non-ideal case, we assume that RD is not infinity. We still assume that R naught is 0, and we are assuming a very large value of A. Okay, so R naught is assumed to be 0, ideal case. So input resistance, again without going into the derivation, input resistance under the non-ideal condition is given by this equation, 1 plus A times beta. Again, beta is feedback factor, which for this amplifier, remember, was Ri over Ri plus Rf. And A is the open loop gain, which you can assume 200,000, you can assume 100,000, whatever you want. And Rd is input differential resistance. And remember, the value for the typical value for 741 is about 3 mega ohm. Minimum value was about, let's go back and confirm it, 2 mega ohm. Typical value is 2 mega ohm and minimum is 0.3 mega ohm. So again, if you look at that right here, if we look at that, A times B is going to be a very large value, Rd is a very large value. So if we multiply, let's say 2 mega ohm to exponent 6, right? Oh, it's right here actually. Assume beta to be 0.01 for a closed loop gain of about 100. A is 200,000, Rd is 2 mega ohm. That R in non-ideal will approximately be equal to 40 giga ohm. So I mean, 40 giga ohm is as big as infinity, I would say. Really, no current is going to flow through 40 giga ohm resistance. It's just almost open circuit. So again, should we use this? Should we just assume it's infinity? I would say let's just assume it is infinity. I mean, this resistance is as big as infinity. So again, you can see that at DC or low frequencies, the ideal value of input resistance of the non-inverting amplifier is pretty much close to the ideal value, which is infinity. Finally, the output resistance. The output resistance in the ideal situation is 0. It's the same thing as R out of the amplifier ideal value. So it is 0. R out ideal is equal to R out of ideal R out of the operational amplifier, and ideal R out value is 0. Alright, for non-ideal case, basically the way we calculate it is through this circuit, which is the Thevenin equivalent circuit. We put a source at the output, test source at the output, which we're calling it Vx, and then that test source is going to run a current Ix, and the ratio between Vx and Ix is going to be the resistance that this source is going to see, or the Thevenin resistance, which in this case is the output resistance, because it is connected in the output port. The source is connected between the output port. Again, we discussed that in circuit analysis too, how to apply the Thevenin circuit. There were three methods to apply Thevenin circuit, and this is the third method or second method, whichever. I think this is the third method, sorry. So we short circuit all the input voltage sources, and we apply a test source at the output, and we measure the ratio of the current of the voltage source to the current coming out of voltage of the voltage source to the current coming out of the source. So when we do that, Vx over Ix, we will get R out over 1 plus A times beta. Once again, A times beta is extremely large. Beta is, let's say, 0.01, A is 200,000, is going to be a very large value, and R out is about 75. This is not watt, sorry, this is ohm, 75 ohm. So your output resistance, if I use these parameters, your output resistance will be 37.5 milliohm. Extremely small. Should we assume it is approximately equal to 0? Why not, right? No harm. So this is an example 3.1. Go over this example, and it's pretty straightforward. I don't really have to go over that. So in the next video, we're going to discuss the non-ideal case of inverting amplifier.